What's up guys, my name is Cherno. Welcome back to the ray tracing series. Okay, so we're rendering a sphere. Great. But you know what's better than a sphere? Two spheres. What we're going to talk about today is how we can have many spheres in our scene. And in fact, what even is a scene and how do we structure that? The theory behind rendering multiple objects is rather simple. If you haven't already, I encourage you to actually think about it. Stop this video right here and try and actually think through how you would do this yourself without me intervening and showing you. I think it's really important that pretty much every step of the way in this ray tracing series, you try and actually think and do this work yourself. Trying to figure out things for yourself, even if you end up with a worse solution, is always good. So get into the habit of doing that if you want to learn. At the moment, inside our viewport, we basically have this definition of a camera that shoots rays into a specific direction and from a specific origin, from a specific point. We also have mathematically the description of this single sphere. All we do for each ray is just see whether or not it actually intersects this sphere. And if it does, then we take the calculations a step further to figure out like the hit position and from that the normal and all of that stuff, and then eventually return a color. If we dial back that process a little bit and we just think about what we actually do to work out whether or not we hit the sphere, we do some math involving the ray and then this mathematical description of a sphere, which is really just its position and its radius. In fact, we haven't really touched the position of this sphere yet. We can't really move this sphere around. That's also something we'll talk about today. So with that concept in mind, if we want to have multiple spheres in our scene, we just need to do that ray versus sphere intersection test multiple times. If we have two spheres in our scene, then for every ray that we fire from the camera, we just need to see whether it intersects sphere A or sphere B. Now, if that ray intersects both spheres, because like one's behind the other one, then we need to figure out which one is closest to the camera. And that's the one that we'll evaluate. And that's it. That's really all there is to it. Obviously, if we don't hit anything, we just return like our background color. If we do hit a sphere, then whichever sphere we hit, that's the one whose color we'll return and do the lighting calculations on. Now, this is obviously like the simple case for what we have here at the moment, which is a very simple ray tracer. When we get a little bit deeper and we have, for example, translucent materials, then obviously we might want to render one sphere in front of the other sphere. Like if we go through glass, we probably want to keep going so that we see the sphere behind our glass sphere. But for now, let's keep things simple. So if we take a look at our code, if we take a look at our trace ray function, this is the function that's effectively drawing the image we just saw, there are two really important parts here. There's the first kind of step, which calculates the discriminant, which tells us whether or not we hit the sphere at all. That's going to be important to do per sphere, because obviously if we didn't hit the sphere, we don't want to waste time calculating the rest of this. However, over here we have that closest t variable. This is the closest hit position to the camera. This effectively gives us the distance of the sphere surface that we hit from the camera. We need to make sure that if we do successfully hit a sphere, we do this calculation for each sphere that we hit along that ray. And since this gives us the distance of the hit, whichever sphere returns the lowest closest t position, that will be the first sphere that ray hits, and thus that is the only one we care about evaluating for now. After that, we can proceed and calculate the hit point, the normal, the light direction, and the actual sphere color and return it as an actual pixel color. Now, if you're not quite understanding all of this math, then I highly recommend that you check out the sponsor of this series and this video, Brilliant. Brilliant is an amazing website filled with courses on various STEM topics, such as like literally all of the math we'll be using in this ray tracing series. I get a lot of questions from programmers asking whether or not math is important. Long story short, yes, it is. But whilst you might be able to not get too deep into math if you work in other areas of computer science, if you're in graphics programming and like doing stuff like this ray tracing series, there's no way you'll get by without understanding the math. And if you do, it'll be very sad. Whilst Brilliant have a number of advanced math topics such as calculus, which we'll be using later in this series, if you're new to math and you find it a little bit intimidating, then Brilliant have this brand new everyday math course that you can start with. It's a really nice way to kind of ease into it before you can move on to, say, algebra and then maybe later calculus. Now, why do I like Brilliant so much? Why not go to some other math course website? What makes Brilliant really good, in my opinion, is the fact that it's extremely visual and interactive. Seeing how things work visually is my favorite way to learn. I think a lot of people will probably agree with that, but aside from just showing things visually so that you can understand how things work, Brilliant also get you to engage with it. They give you these nice controls that you can play with, and once they've taught you something, they quiz you on it to make sure that you actually understand what's going on. The best thing about Brilliant is that you can get started for free. Just go to brilliant.org/the Cherno, link will be in the description below. And if you do enjoy it, then for the first 200 subscribers, Brilliant is offering 20% off an annual membership. Huge thank you to Brilliant as always for sponsoring this video. So now that we've kind of determined which part of this math needs to be done in order to figure out whether or not we hit a sphere and which sphere is the closest sphere, let's talk about how we can actually structure a scene. Now there's many different ways to do this, and I just want to stress that like when we learn things in this series, we start off really gentle. We want to keep this as simple as possible. There's no reason to complicate anything at this point in time. However, obviously we can get fairly complicated, and we probably will as the series goes on, because for example, if you have 1,000 spheres in your scene, then you can't simply loop over every single sphere to see if it hits or not. That will be way too slow. I mean, you can, and of course if this is like an offline renderer anyway, then maybe waiting 10 minutes or whatever is fine for you. But there are, of course, faster ways to deal with larger scenes, such as like some kind of spatial partitioning system. If the camera is facing that way, we don't really care about spheres behind us, so why would we consider them at all? We wouldn't. Feel free to extend what we've got here beyond what we're covering. In fact, I encourage that. It's a really good exercise, obviously. However, I also want to keep in mind that because the end game of this series is to move this onto the GPU and actually use like ray tracing shaders for this stuff, I don't want to spend too much time talking about like scene side optimization, because the way that we represent this in acceleration structures later on is going to mean that we just throw away all of this code. That's not to say we won't be optimizing the CPU side of this renderer, but just not straight away. Okay, so let's talk about a scene. So what I'm going to do is, if we come over here into source, let's just add a new item. I'm just going to add a new scene.h header file, and this is simply going to be like a representation of our scene. We're just going to make a struct called scene. We're going to keep it really simple. It's just going to contain a vector of spheres, and we haven't really defined our spheres yet, so let's go ahead and also create a struct called sphere, and this is going to contain some kind of position in 3D space, as well as a radius. Now I'm going to give it a default radius of 0.5 so that we have like a 1 meter diameter sphere. And then I'll also give it a default position of 0, 0, 0 so that we're initializing these variables. Let's go ahead and include both GLM and also the vector header as well. And that is like literally all that we're going to add, because that's all we need for now. Actually, I lied. One more thing I want to add to this is the color. So let's go ahead and add the color, which we're going to call albedo. Why are we calling color albedo? Why not just call it color? Because albedo is technically like the non-lit diffuse component of a material. And since we'll be kind of creating a physically based renderer here, we're going to try and use the correct terms. I'm actually going to just set this to white. And actually, let's remove these because we don't need them. Okay, cool. So we have a white sphere that is 1 meter in diameter by default at the origin. Cool. Now, one thing I want to do before we kind of move on and create this scene here is I actually want to talk a little bit about the position of our sphere and how that works, because at the moment, we have just been assuming that the sphere is always at the origin. Now our camera can still move around. That's our ray origin. That's the camera position, effectively. However, what happens if we want to actually move like the sphere around? How does that work? Well, if we come back to our math, then we remember that the equation of a circle is this: x minus a squared plus y minus b squared minus r squared. Now we only cared about the x and the y. We only took x and y when we plugged everything back into our actual equation here. Why did we do that? Because A and B represent the position of this circle or sphere. A is the X component of the position and B is the Y component of the position. And if we just make those 0, then of course X minus 0, Y minus 0, that just gives us X and Y, and that's good enough to use. Now is the time that we have to go back and actually do this subtraction. We need to do this subtraction before we plug it into the rest of our equation so that we can move the sphere somewhere and not just necessarily have it always in the origin. Now you could of course plug this back into the math equation and work everything out, and that's totally viable. However, I think there's an easier way to think about this problem. If this is our camera that we're rendering everything from, so this is like the origin, right? This is our ray origin over here. And then we have a sphere, but the sphere is not at the origin like it currently is. Let's just say the sphere is over here. This sphere might have like, let's just say we've moved it left. So this is like a top-down view of the camera. If we've moved it left, then maybe the X is now -2, whereas it used to be 0 over here in the origin. The thing about cameras is that cameras don't really exist. They exist in terms of our code and when we actually calculate the math, like they have to in some form. But don't forget that at the end of the day, what we're actually drawing is pixels on a screen. This screen does not physically move anywhere. All we have to determine is where objects lie, like within this screen. So what I'm trying to say is that if we have like a sphere in the middle and we move our camera to the right, what we're actually kind of doing is within this, we're moving the sphere to the left, right? Because if I draw the sphere over here again and you pretend this sphere doesn't exist anymore, it's like the camera has just moved to the right. Because of this, because we're really just translating objects within this kind of square, it doesn't really matter if our camera is the thing that's doing the moving or if it's the objects doing the moving. Because at the end of the day, the camera just determines which objects we're looking at and where they are within our screen. So what that means is if we look at this equation and we take a look at the ray origin, remember the ray origin is our camera's origin. That's where we shoot rays from. What happens if we play with the location of this ray origin? So instead of firing rays this way, what if we move the origin somewhere else, say over here, and now we just fire rays that way? Then check this out. Our sphere has like magically transported into the origin now. And that kind of summarizes how this math is going to work. If our sphere moves to the left by 2 units, what we need to do is kind of like move it back into the origin like this, so that when we look at this original ray origin equation here, you can see that this sphere now is back at 0, 0. And that is actually what this like -a and -b is doing. That's why it's a -a and -b and not like +a or something, because what we're doing is if the circle is at like 2, 2, for example, that's the coordinate of the circle, we subtract 2 from both of these to actually translate that circle back into the origin. And it's the exact same concept with our sphere. So basically, we just need to take this ray origin and subtract the sphere's origin from it and use that in place of everywhere that we use our ray origin. So let's go ahead and write glm vec3 origin. This is going to be like our new origin, and we're just going to write ray.origin minus whatever our sphere origin is. Now let's try and translate that pink sphere to the left by 2 units. So what I'll do is I'll write glm vec3, maybe actually 0.5 because I don't know how much will fit onto the screen. 0 and 0. Now that's positive 0.5, so that will actually move it right. So let's go ahead and move it left by writing negative 0.5 here. So effectively, we're just adding 0.5 to the x component of the ray origin. And this is the origin that we're going to use instead of ray.origin. So let's go ahead and replace ray.origin with just origin. Now let's hit F5 and see if our sphere is to the left. And you can see our sphere has in fact moved to the left. Now, some things have happened to the lighting, and the reason for that is because if we look at the rest of our code, you can see we're still actually using ray origin one more time down here. So let's go ahead and replace that with origin as well. And there you go. Now our sphere is perfectly lit as it was before, but it's now on the left. And just like that, we can move our sphere anywhere we want in 3D space. Cool. So let's have some fun with this. Let's make some kind of control over here in our UI that will actually let us translate this sphere in real time. But first, let's change our renderer to work with this new kind of scene structure, because that will enable it to be aware of all of these properties. If we come back into this header file, what I'm going to do is include scene inside renderer.h. And then when we render something, what I'm going to do is actually have it take in a scene. So let's type in const scene scene and then const camera camera. Now, next episode, we're actually going to talk about the structure of this renderer and how it's going to work. So for now, we're going to stick with this design. However, this is going to change completely next episode. I'll also paste in the const scene scene into trace ray because we're going to need this here as well. So we're not going to have any kind of like persistent scene inside this class. We're just going to pass it around here into the required functions. Let's go ahead and pass scene over here into trace ray. And so now inside trace ray, we actually have our scene instance, and that contains all of our spheres. So now what we can do is let's just grab the first sphere. So first of all, if there are no spheres in the scene, So if scenes.spheres.size is 0, let's go ahead and return our clear color, which is this, because there's literally no spheres in the scene. And then what we'll do is we'll just grab for now the first sphere. So sphere equals scenes.spheres, scene.spheres 0. And now we can obviously access the sphere's position. That's what we're doing here, as well as the radius of the sphere, which is what we'll square instead of just radius. So we can delete this 0.5 radius we were using. Let's also delete this ray direction. We don't need that. And then finally, instead of returning pink as the sphere color here, let's go ahead and set the sphere color equal to sphere.albedo. Okay, so I think that's all of the variables, the temporary variables we were using now replaced. If we go back into our main kind of file, which is walnutapp.cpp, we can actually add that scene into here. So let's go ahead and write scene scene. It should all be included because renderer.h includes scene. That's the scene that we're going to pass into the renderer, and let's just test it out as is. So we should just see a black screen because obviously there are no spheres to render. Okay, cool, we get a black screen. I was just mainly making sure that it didn't crash or anything like that. Over here inside the constructor, this is where we can set up our scene. So let's go ahead and write mSceneSpheres.pushBack, and we can push some kind of sphere into here. So let's go ahead and try and recreate that same sphere. We can just use like an initialize list to construct this instance. We know it's position, radius, albedo. That might make it a little bit difficult to read. So we could set like the position to say 0, then the radius to 0.5 because that's fine, and then we can make it pink by writing code like this. That is a little bit difficult to read though, so you could of course just write it out normally. I'll show you what normally means in a minute, but you can see we get our sphere. So by normally, I mean, I don't know why I said normally, everything's normal, right? But basically what you could do is just push back a sphere like this, and then just set the parameters like so. So we could set the position to like 0, 0, 0, obviously set the radius to whatever you want. The advantage of doing it this way is, first of all, you don't need to set all of them, so you can keep, you know, whichever one at its default. So if you didn't want to set the radius, you can just skip that and just set like albedo to, for example, pink, and then just not set the radius. That's fine. But also obviously we have the names of these variables in these lines of code. Whereas here, like we have no idea, like is this the translation and that's the color, or maybe it's the other way around? We don't know. That's why like ultimately I would encourage you to kind of do it this way. Performance wise in this case isn't really going to matter either. So I guess let's write it out this way, even though part of me probably would write it the first way, just because it takes up a little bit less code, a little bit more concise, but I think that this will be better. Okay, cool, and I'll even add the radius here just so we can see. Now what I'm going to do at this point is actually add some controls so that we can play around with this. Inside on UI render, we have a settings panel, and that's great. What I'm going to do is copy it in its entirety, and I'm going to change the name here to scene. And this is just going to be a nice little panel that we can dock that will let us control the spheres in our scene. So let's get rid of this. And what do we really want to control here? Well, we have 3 parameters. We have position, radius, and albedo, so let's do that. Let's go ahead and just add a control for the position. So this will be a drag float 3. We're going to give it a label of just position for now, and then GLM value pointer with that sphere.position. Now this also lets us pass in a speed. That's how quick we want to adjust that value when we actually drag it. So I can type something like 0.1 in, and then a minimum and a maximum. We're not really interested in a minimum and maximum, so we'll just end it there. Now to use value pointer, you just need to include GLM, GTC, and then it's like type pointer like that. And then obviously sphere.position, like what on earth does that mean? Now, ideally what we would do here is we would loop through every single sphere that we have in our scene. We ultimately only have one for now. So let's go ahead and write scene.spheres 0 for now. We'll change this in a minute just to test out our position. Let's go ahead and also add a control for our radius. Now clearly that's not a 3-component float, so we'll just rename this to be just a drag float with that single float. We don't need this value pointer. Instead, we're going to pass the memory address of radius, just like that. And we can keep it at 0.1, sure. And then finally our albedo, which is our color. So let's rename this to be a color edit 3. That will give us a nice color picker, and then we'll pass in the albedo like so. Okay, so we should now be able to fully edit all of the parameters of that single sphere that we have. So if we run our program, we can see we have this scene panel. It's brand new. Let's go ahead and dock it like up here maybe. I'm just going to go ahead and resize this a little bit to make it smaller. Okay, so we have position, we have radius. So let's go ahead and try and move this. Check this out. We can move our sphere in real time. We can make it be further away with the Z. Now you'll notice, by the way, if I go positive here, we see the sphere but upside down. That's because the way that we're actually processing, like the closest t, we're not really caring about if it's negative, and that's why we kind of see this. All you have to do is just discard the pixel if that closest t variable is negative, but we'll implement that a little bit later. But otherwise you can see we can push it further away, move it up and down, move it anywhere we want really, everything works, which is great. We can make it bigger and smaller by adjusting this radius, which is pretty cool. And then finally we can play with the albedo and set it to, let me just move this over here so you guys can see. We can just play with the albedo and set the color to whatever we want, okay? As simple as that. Now, let's go ahead and talk about how we can have multiple spheres. So to start this off, what I'm going to do is simply push another sphere into here. So in order to have these two kind of spheres here with the same variable name, I'm just gonna add a little scope, just like that. So we're pushing back two spheres. Now at the moment, we're doing this kind of all manually. You probably wanna have some kind of like scene file description maybe. You could also add UI to actually add these spheres so that you can do it while the application is running. I'll leave that for you guys to do for homework. But otherwise, what I'm gonna do is just push this back a little bit because I wanna kind of make sure that we get the one sphere in front of another sphere working correctly. So if I just take this and set it back to like -5. Remember, negative Z is the forward direction, so I'm pushing that back. Might move it like a little bit maybe to the right, and then I'll also make it be a little bit larger, 1.5, and maybe we'll make it blue. So I think I'll make it like a nice kind of blue, 0.2, 0.3, and 1. Okay, cool. So we have two spheres now. Which one is it going to render? Well, if we look at our code inside the renderer, we obviously know that it's only ever going to render that first one. If we flip back and just reorder these, then we should see just the blue sphere. And that's what we see. Okay, so it does look like it would be obscured a little bit by the pink sphere if we just had like the pink sphere in front of it as we currently do. So that's good because that's kind of the result that I'm looking for. So now let's just make this work with multiple spheres. How do we do that? Well, back in renderer, we just need to loop through all of these spheres and determine which of them has the lowest closest t value. So which of these two spheres, if we hit it at all, is the closest sphere to the camera, and then we'll continue evaluating that. So let's go ahead and write a for loop here that's going to go through every single sphere. I'll just write a for each loop like so. And then this really is going to like contain the rest of our code. But first we do need to determine whether or not we hit anything at all and which sphere is the closest sphere, because we obviously can't evaluate any lighting until we know which of these spheres is the closest sphere. So let's go ahead and just make a little pointer here called closest sphere. And I'm going to set it equal to null pointer. This will just hold like the pointer to whatever sphere we determine is the closest sphere. And if it's null pointer, then we know we haven't hit anything. So then for each sphere, what I'm going to do is go through basically all of this code, right? Because we determined this is the code that needs to be evaluated to work out our closest hit. Now, if we take a look at this, there's a few things going on here. First of all, we're returning. We don't want to return because what this will currently do is if we miss the first sphere, then let's say we just return our clear color, but there could be another sphere. We have to loop through all of the spheres in our scene before we're sure that we didn't hit anything. So because of that, if the discriminant is less than 0, all we're going to do is continue. That will just move us on to like the next sphere. Now, if we did actually hit something, right? So in other words, the discriminant here is greater than 0, which means that we've hit something or is equal to 0. We want to make sure whether or not this closest t is like the closest so far. And if so, then this is in fact our closest sphere. We can't just go ahead and assign closest sphere to sphere. In fact, let's make this a const sphere, because obviously this is now no longer checking if it's the closest sphere or not. This is just going to set our closest sphere to be the last sphere that we hit within this list. So what we need to do is kind of maintain our hit distance over here. We'll set it to like the maximum possible value for a float, which I like to just type in FLT max for that. You can use std numeric limits float max like that. Maybe I will do that, I don't know. This just takes up so much space compared to this one little macro that's just defined to this. So honestly, that's why I kind of use it, but technically I guess maybe so the C++ community doesn't kill me, this is like the C++ way to do this. What I'm doing here is just setting this hit distance to be, again, the maximum possible value of a float. That means that obviously these hit distances are guaranteed to be less than that. So what I'm going to do here is just check to see whether or not closest t is actually less than whatever our current hit distance is. And if it is, I'm going to set closest sphere to sphere and also update our hit distance with this closest t. And that's all there is to it. Now the good thing is we obviously retain this, so we never need to do this calculation again. We've got this hit distance. This is our second hit point, which I'm going to drag up here, but that's not really used. So I'm just gonna leave it commented out so that it doesn't confuse anyone. And then since closest sphere is originally set to null pointer here, we know that if closest sphere is still null at this point in time, then clearly we haven't hit anything. So if closest sphere equals null, return, and we'll return our glm vec4 0 0 0 1. Okay, so that's the same thing that we used to be returning here if the discriminant was less than 0. However, now we need to check each discriminant, obviously, for each sphere. Okay, cool. So now what do we have to do? Well, we just need to continue this calculation. However, the sphere that we have here is now going to be our closest sphere. Now we also need origin, as you can see. If you scroll up a little bit, we do this calculation up here. So we need to do it again, but now it's going to be done for the closest sphere, obviously. So if I come down here and just write origin, we're going to write closest sphere position, like that. Closest t is going to be our hit distance. And then obviously sphere albedo is going to be closest sphere albedo, like that. And that's kind of it. It's really quite simple. So now let's go ahead and run this code and check it out. That's it. Let's move our camera around, and you can see we now have 2 spheres in 3D space. Now we can still only edit one of them, so let's go ahead and fix that. If we go back into our main file here, walnut app, I'm going to change this a little bit so that we actually iterate through all of the spheres inside our scene. And I'm going to write this out as a for loop. You'll see why later, instead of just using a for each loop. So m spheres size I++. We'll surround all of this inside that for loop here. And then of course, instead of scene.spheres, and then of course, instead of mscene.spheres 0, it'll be mscene.spheres I, because I is the index. Now I'm actually gonna pull this out a little bit, and we're just gonna write sphere equals that. That way I can just kind of create an alias for it so that I don't have to keep writing out the full name every time. And that theoretically should work, so let's just hit F5 and see what happens. However, if I try and adjust this, you can see it actually adjusts both of the sphere position. Same with like the radius. What's going on here? The problem here is actually with IMGUI. The way that IMGUI identifies each control is by its name. I mean, not necessarily just by its name, but in this case, it's identifying it by its name. Because these names are identical per sphere, so in other words, as we're iterating through this, we're actually creating 2 drag flows within this scene window called position. And when we start interacting with one of them, IMGUI doesn't know which one we're interacting with because they've both got the same ID. To fix this, what we can do, or the easiest way probably to fix this, is to just do IMGUI push ID and set kind of like, this is almost like setting like a namespace for this particular block of controls or widgets. So if we just push ID I, and then we pop it at the end of the iteration, because this I variable is going to be a unique index for each sphere, that means that this first iteration will kind of be like position index 0. And then the next one will be also called position, but it'll be like within index 1. So it will have a different ID. To make this look a little bit nicer, I'm also going to go ahead and add a separator between each iteration. So if we launch this, now you can see we have a nice separator between these, and hopefully when we adjust them, it now only adjusts one of them. And we can move this back and forth. We can change like the color to whatever we want, the radius, and you can see we can have a nice big one here. And more or less, we have multiple spheres rendering in our scene. Now our render time has of course increased because now we're shading more pixels and we also have to evaluate more potential spheres, but hey, that's life. There are some optimizations we can do already to the math, so go ahead and maybe try and explore those if you're interested. Just try and look at the code and see if you can come up with anything that doesn't necessarily need to be done potentially. But otherwise, next time will be a bit of a restructuring episode. We're going to talk about how we can kind of scale this a little bit because we're doing everything inside that one trace ray function. That's going to make things in the future a little bit more difficult. And also I want to structure things in a way that's going to be a little bit more like the GPU way that we end the series with. So thank you guys for watching. Hope you enjoyed this episode of the ray tracing series. Don't forget that every episode is pushed to GitHub in a separate commit, so all of the code is available there for free for you guys to check out. Go ahead and brush up on your math and support the series by going to brilliant.org/thecherno, and I will see you guys next time. Goodbye.